Okay, in this video we're going to discuss the difference between efficiency and capacity factor. They're similar in that they both pretty much mean that a power plant's not going to be operating at 100% efficiency, or at 100%, I should say, but for different reasons. Capacity factor I think is easier to understand, so we'll talk about that first. Okay. Capacity factor is literally it's the amount of time the plant's operating. So the fraction of time a power plant is operating. So here's my two power plants. The first one, the geothermal power plant, they have a very high capacity factor because they draw their energy from nuclear decay in their Earth's core, which never stops. So their energy source is continuous. They still don't operate at 100% capacity though, because maybe they have to be shut down for maintenance or repair or improvement, or maybe they shut down on their own because it's not peak demand and they have nobody to buy the electricity, so why bother producing it? But it's still pretty high. They have a capacity factor around 90%, so 0.9. Wind farms, on the other hand, tend to have pretty low capacity factors because you can imagine the wind doesn't always blow. And if it's not blowing, you have no energy input. Or they even have to be shut down if the wind's blowing too much because they can be damaged. And then, of course, routine maintenance and whatnot. So wind farm capacity factor is somewhere around 25%. Could be higher or lower depending on location. So 0.25. So that's capacity factor. Let's do one quick problem. It's very simple. We'll talk about a nuclear power plant, which also runs at very high capacity, because once you have the nuclear decay going, you don't usually want to stop it. But sometimes they have to for maintenance and whatnot, and safety requirements. Okay, so you have a 1 gigawatt nuclear power plant, but it operates at only 91% capacity. How many kilowatt hours of electricity will you produce in 1 year? So pretty straightforward problem. Here's our 1 gigawatt of power. A gigawatt is the same thing as 10 to the 6 kilowatts. Notice we want to convert it to kilowatts because we need to relate it to kilowatt hours. We're running at 365 days a year, 24 hours in 1 day, but not really. We have to reduce that by the capacity factor. So multiply by 0.91. So days cancel out, and gigawatts cancel out. We're left with kilowatt hours. So it comes out to 7.97 times 10 to the 9th kilowatt hours. So that's it. This 91% capacity is right here, and it shows how this number should have been a little bit higher, but it's reduced because of reduced capacity. So capacity factor is pretty straightforward. Okay, efficiency. Efficiency is a different issue. Efficiency has to do with the second law of thermodynamics. And you can talk about efficiency in all kinds of things. Photosynthesis efficiency, efficiency of humans eating food and creating work, but we're going to talk about it in terms of power plants. Specifically in terms of when you input some kind of fuel, and we'll say electric energy is our output, and you output some electric energy, you are not going to get out 100% of what you put in. It's a simple law of thermodynamics. It's impossible. Let me explain a little bit about why. Here's my little power plant. This is my turbine. This is my generator. And the turbine is literally just some kind of paddled wheel thing that turns. And as it turns, it's connected to this metal coil, which turns in between giant magnets. I'll indicate them by north and south. So you've got an electromagnet going on here, and you produce electricity. Very simple law of physics. Okay. What turns this turbine? You could have a wind turbine is literally the turbine. You could shape it like a wind turbine, and that's what turns and creates the electricity. Or you could have an old-fashioned water wheel turning and connected to an electromagnet that produces electricity. Or you could have a dam where water falls through the dam and turns the turbine and generates electricity. But I want to talk about what happens when you use a fuel. So say you use some kind of fuel like coal, a fossil fuel, oil, or natural gas. Or actually we could even talk about nuclear fuel. So you burn one of these fuels, or in case of nuclear reaction, you allow the nuclear decay to go on. And the basic premise is you have some giant vat of water and you heat it up. You boil the water by burning your fuel, and you produce steam. And this is the steam. You use the steam to run over the turbine and turn it and go through the electromagnet and produce electricity. And that's basically how a power plant works. And you can see where you're gonna lose efficiency. You're gonna, no matter how well you insulate your water, you'll lose excess heat off of here. In the pipes, you'll lose excess heat. In the turbine, you'll lose excess heat. There's constant heat loss in all sorts of places, and it's literally just waste energy. And you will never have thermodynamics. You'll never have 100% efficiency. Okay, let me give you a quick example in a coal-fired power plant. You can see all this coal coming in. It's going to get burned, produce steam, turn a turbine, go through an electromagnet, and produce electricity. A ton of coal has about, depending on the type of coal, has about 24,000 megajoules of chemical potential energy stored inside of it, inside the chemical bonds of the coal. But when it's run through this power plant, the amount of electrical energy that's produced is much lower. Only about 8,400 megajoules of energy will be produced. So you can see the loss of efficiency. And these are typical numbers for a coal-fired power plant. So 8,400 megajoules of energy only produced. So you have an efficiency of only 35%. Literally meaning 65% of the coal's energy was lost to waste heat. You can imagine this in a car. Similar scenario in a car. You put gasoline in a car and burn it, and you want to make the car go forward, but you lose massive amounts of heat energy. There's heat coming out of the tailpipe. That thing gets really hot. The engine gets incredibly hot. It's all waste heat. You even have friction in the tires and all this waste heat. And in the end, the internal combustion engine of a car is only about 20% efficient. 80% of the gasoline's chemical potential energy is lost as waste heat. Okay, so let me do two problems with efficiency. They're a little bit more complex than capacity because you have to take into account the fuel. So you have the fuel input and the energy output, which makes it a little complex. All right, first problem. We've got a ton of coal. It's got an energy density of 24,000 megajoules. If it's burned in a power plant at 35% efficiency, how many tons will you need to be burned to supply one home for the winter? assuming the home requires 120 megabTUs of heat energy. So we have several things going on. We have to take into account this efficiency issue, and we have two different units for heat energy. We have BTUs and we have joules. So we're going to have to do a conversion there. So let's start out by dealing with our efficiency here. We just did this, 24,000 megajoules of energy stored in that coal, but at only 35% efficiency, you're only going to get out 8,400 megajoules of energy. So now let's convert this to BTUs and see how it stacks up. So 8,400 megajoules of energy. We know 1 megajoule is 10 to the 6 joules. And you know 1,055 joules in 1 BTU. So megajoules cancel, joules cancel, and we're left with 7.96 times 10 to the 6th BTUs. So this is how much energy our coal is supplying. 10 to the 6 is mega, so you can see this is 7.96 mega BTUs. So a ton of the coal is providing about 8 mega BTUs. You can see that's not enough. It's not nearly enough. The home needs 120 mega BTUs. That ton of coal is only providing about 8 mega BTUs. Do a simple ratio, and you can see in order to heat this home, you're going to need about 15 tons of coal. You're going to need to burn about 15 tons of coal to heat this. It's quite a bit. Okay, let's do another one, a very similar one, using wood and a wood-burning stove. Some of you might have at home. Okay, in this one, we're saying that a cord of wood has an average energy density of 20 million, or 20 times 10 to the 6 BTUs. If it's burned at 72% efficiency in a wood-burning stove, how many cords of wood would you need to buy to provide 120 megabTUs of heat for the winter? So it's a very, very similar problem, just a different efficiency and a different energy density. You can see wood-burning stoves are much more efficient. Much more efficient than fireplaces. Fireplaces actually can have a negative efficiency. They actually can draw heat out of the house. But a wood-burning stove is pretty efficient. Alright, so let's take into account this efficiency. Here's our wood density. By the way, some wood has a higher density than that. If you don't let wood season and dry out, it will be much lower. So wood varies significantly. I'm just using this number as an average. So 20 million BTUs of energy in this cord of wood at 72% efficiency. You can see we'll get 14.4 times 10 to the 6 BTUs of heat energy out of this cord of wood. 10 to the 6 again is mega, so 14.4 mega BTUs of heat energy we'll get out. And same ratio, 120 mega BTUs needed in the home, 14.4 mega BTUs from that cord of wood. You're going to need to buy 8.3 cords of wood for the winter in order to heat your home. Alright, that's capacity factor and efficiency.